Let us continue our discussion on the equilibrium for two phases. Now, as we have seen in the last lecture, lecture 10, we have seen that how we can find out the chemical potential of a particular component in a particular phase with the help of slope of G2 line. So, in this lecture, which is lecture number 11, we would see that y common tangent talks about equilibrium between two phases, or rather y does, if I write talk about equilibrium between two phases. Now, we have seen in our last lecture that at any point on G2 line we can get an equation for G2, which is G2 equal to x a mu a plus x b mu b. Now, in case of solid solution it would be solid, and in case of liquid solution it would be liquid. Now, whenever we talk about equilibrium, and that too when we have composition as a variable, now that time we can write G in the form of function of P, T and composition, and these compositions can be written in the form of N I, and that time we can write it as del G equal to plus summation of J, and this is basically nothing but mu I of number of components. So, this is the ith component chemical potential of particular phase. This is phase or solution, whatever you say. Now, if pressure and temperature are kept constant, then the entire equilibrium situation is decided by this particular term, chemical potential. If we have pressure constant, means it has already attained mechanical equilibrium, temperature constant means thermal equilibrium. But if we see that the chemical potential of a particular component in a phase 1 is same of that particular phase chemical potential in the second component, then we will say that the system is in chemical equilibrium. So, the concept of chemical equilibrium is mu A phase 1 equal to mu A phase 2, and that time we say that phase 1 as well as 2 both have component A. And similarly, if we try to see the chemical potential of all the elements of phase 1 and 2 in these two different phases are same, we can say that the system is in equilibrium or the chemical equilibrium. The same concept can be valid here. Now, let us try to see the concept what we have just now stated. And here we are trying to plot chemical potential GA 0 P1 and this is GB 0 P1, and now I can put it as this one as GB 0 phase 2 and this is as GB 0 phase 2. Sorry, this should be A because this is pure A side. This is pure A and this is pure B. Now we can get the G1 plot for both the phases. This is G1 of P1 and this is G1 of P2, and correspondingly we get the G2 values of phase 1. Let us say this is my G2 phase 1, and if I try to plot it in a different color, this is my G2 phase 2. G2 phase 2, and we see that they are not lying on the same free energy line, same free energy values. So, they have two different free energies. Now, I can draw a tangent at different points on this particular line, and accordingly we can get the chemical potential mu A phase 1, mu B phase 1, mu A phase 2 and mu B phase 2. So, we can get all those values. For example, if I try to see a tangent on this particular line, so this is the composition, this is let us say XB1, and that time this becomes mu B phase 1, this becomes mu A phase 1. Similarly, I can try to get, if I try to plot the tangent at this point, which is let us say XB2, I can get the chemical potential values also. This is mu A phase 2, this is mu B phase 2. And from our previous discussion, we can also change the concentration reversibly from one point to another. So, actually if I am here, I can go to this particular point by adding B atom reversibly to this particular concentration XP1, or on the other hand I can also start with this particular concentration, I can go to this particular concentration by taking out B reversibly from this composition, or adding A to this composition, So, that means all the time I can have this reversible process in order to maintain the system is in dynamic equilibrium. Now, as we take this particular tangent, this particular tangent, and if I try to shift it, like if I try to rotate that tangent over this particular curve, I will come across at certain situation where I will get a tangent which will become tangent to this point as well as on this graph this point. Okay. So, this is that point and this is the point, and the composition, let us say here the composition is with the red color, I can mention it as xb3, and at this point the composition will be little on the left side, sorry, this composition would be little on the left side. So, this is that composition, this is xb4. Now, let us look at these 2 points. One interesting fact is, at this point I see that mu A phase 1 and mu A phase 2 they are merging on a particular point at this point. Similarly, at this point I see that mu B phase 1 and mu B phase 2 they are at the same point. Now, at this composition which is xb3, I can have an equation for G2 and for what phase? P1 phase. P1 phase I can write it as XA3 phase 1 mu A phase 1 plus XB3, since we are considering only this phase 1 and mu B phase 1. Now, if I try to change this particular concentration of phase 1 to this composition which is xb4, I have to simply add B into this composition reversibly. So, as we have seen in our last lecture where we have considered this particular equation which is G2C equal to C is nothing but 1 minus C mu A plus C mu B, and that was changed from so in order to go from this to this, I just had to add B reversibly to this composition C0. So, if I try to change this composition of that phase 1 to this particular concentration XB, I can simply write phase 1 equal to, because I am not changing this term and this term because they are fixed. So, I simply can write it as x A 4 of phase 1, because I am not changing the phase, I am just changing the concentration, phase remains the same, mu A phase 1 plus x B 4 P1 mu B P1. So, I have not changed this particular term remains fixed because these 2 points on those 2 pure metal sides are fixed, because I am going along that particular free energy line and I am doing it doing this change reversibly. Now, at this point I can write G2 of phase 2 is equal to XA 4 P2 mu A P2 plus XB 4 P2 mu B, this will be P2, because now I am considering for phase 2. Say if this is equation 1, this is equation 2, I would see that at this particular concentration, I do get two phases, that means P1 and P2, where I could see that their chemical potentials are merging at a single point on the pure metal sides. For example, if I consider pure A, I see that these two particular values are merging at the point. So, that means mu A P1 equal to mu A P2, and here also it is mu B P1 equal to mu B P2. So, if I one minus 2, if I do that, then I do get this equation P1 minus, sorry, this is G2, equation for solution G2 P2 equal to, since the composition is same, XA, I simply write XA 4 because the composition is same at this point, compositions are same, and also I have taken the phase 1 to this composition by adding B reversibly into the P1 of composition XB 3. I can write mu A P1 minus mu A P2, and similarly these two compositions are same. So, XB 4 mu B P1 minus mu B P2. So, if I go to this value, so that means G2 P1 minus G2 P2 equal to XA4, that means composition, mu A phase 1 minus mu A phase 2 plus XB4 mu B P1 minus mu B P2. Since we have seen that mu A of phase 1 equal to mu A of phase 2 as well as mu B phase 1 equal to mu B phase 2, that means G2 P1 minus G2 P2 equal to 0. And remember, this we have achieved by reversible transformation from composition XB3 to XB4, and this one we are maintained at XB4. So, this is reversible transformation. That means that phase 1 and phase 2 both are at equilibrium, because the free energy of these two phases at that particular composition, which is XB0, are same. So, this is equilibrium. Now, we understand that why this common tangent indicates the equilibrium of two phases at two different concentrations. So, this particular clue we will again use it for drawing phase diagram for solid liquid. So, now we will be using several concepts what we have learned till now. One concept is we can get the chemical potential of a particular component at a particular point on the G2 line or G2 curve of a phase by simply getting the slope at that point. That means we can get mu equal to G2 plus xb xa, which is A, and similarly mu b equal to G2 plus xa xb. So, these two equations, as well as we got the knowledge of common tangent for indicating equilibrium between two phases. This is concept number 2, this is concept number 1. So, these two concepts will be essential in order to get a phase diagram, and phase diagram is always drawn as per our current understanding from the equilibrium criteria. Let us get into the phase diagram. And that too binary, solid as well as liquid ideal solution. Now, when we try to get to the phase diagram, we have to physically see where are those critical points. For example, the standard state for solid as well as liquid, whether the temperature what we are considering is higher than one particular pure component and lower than the other pure component, and also their positions. So, let us first consider the pressure is 1 atmosphere. So, we do not have to worry about it. And second consideration, let us say the T which we are considering, the temperature at which we are trying to see the equilibrium between solid and liquid solutions, that T is less than the melting point of pure B, but greater than Tm, which is the melting point of A. It means that if I try to see the melting point axis, this is my Tm A and this is my Tm B. If the T is here, so that means at this T, that is that particular temperature, A should remain in liquid condition because this temperature is higher than pure A melting point, and B should remain in solid form because this pure B melting point is higher than the temperature of our consideration. So, if we try to see the plot, now at the same time I can choose the reference point, and let us say I choose the reference point as 0, that means the free energy, standard free energy value in the, and also whether it is a standard or non-standard, it does not matter, this is the free energy axis. Now, if I take these 2 points as 0, and since as per this particular criteria pure A should remain in liquid condition, that means pure A free energy in liquid state must be lower than the free energy of pure solid, because if we try to see the melting point G versus temperature plot, so this is my TMA and this is GA, this is G of solid A and this is G of liquid A, and the temperature what we are considering is lying somewhere here. So that means standard free energy of pure A in liquid form should be lower than the standard free energy of pure solid at that particular temperature. So if I take it as a reference, so this is GA0 liquid, so then GA0 solid would lie higher. But on the other side it is just reverse, because this temperature is lower than the melting point of pure B. So at this temperature solid B would be the stable state. So that means the solid B standard free energy should be lower than the standard free energy of pure liquid B. So if I take it as arbitrarily, if I choose it as B of solid, so somewhere GB0 liquid will be lying above, and we can immediately get the G1 lines of, this is G1 of solid and this is G1 of liquid. Let us stop here. We will continue this discussion in our next lecture, but at least you should understand that why we are considering 0 point to be ZA0 of liquid and this is GB0 of solid, because we can arbitrarily choose the reference point according to our convenience, and that is what we always talk about standard state, because standard state is taken from the convenient part of it, and which is talking about the reference condition. Thank you. So let us stop here.